All right, so our last example here comes from mathematics in the ancient Greek tradition. We are learning what is called the Theorem of Pappus. Pappus was a Greek mathematician, and this theorem is adapted from some work that he did, although he himself didn't know any calculus. This was long before calculus had been formally invented. That happened much, much later. So here is the theorem of Pappus stated for the general regions in the plane. If there is a region R in the plane, rotated about some line L, and here it's really important actually that they don't intersect one another. The region lies entirely on one side of L and doesn't overlap it at all. So the reason here is that we are going to now rotate this region around the line, and we don't want any doubling up. Okay, so we're going to rotate this region around this line here, and that is going to form a solid of revolution, just like we saw back in chapter 6. So we could try to use the techniques that we learned back in chapter 6 to find this resulting volume, or we can use the now easier version involving the theorem of Pappus. It says that the volume of the resulting solid is given by a really simple calculation. Take A times D, where A is just the area of the region here, which you might be able to find with calculus, right? Take upper minus lower, or however you do it, to find the area of your region. And then D is the distance that's traveled by the centroid of R. So there are many, many points in this region R, and when they rotate around this line L, they all travel a different amount of distance. So for example, if you take a point really close to L and rotate it around L, it's going to go a relatively short distance. Whereas if you take a point that's really far away from L and you rotate it around, it's going to go a very long distance around. So the specific point that you choose means that you're going to travel a very different amount of distance. But the centroid, somewhere in the middle of this shape, maybe right there, is going to travel a special path around the line L here. And if you can measure the length of that path, D, and multiply it by the area of the shape, you will find the total volume of the solid. So this is not necessarily obvious, but this is a really nice way to think about it. Essentially, what we're saying is we're adding up a bunch of copies of this area here, rotated around in a big circle. Multiplying that area times the distance, it's as though we had stretched this out, the distance D here. The amount that we have to stretch it out depends on the centroid of the shape. Okay, so how can we use this? When is this useful here? Well, the example that the textbook uses is from a shape called a torus. So we're going to examine the torus here. Torus is a shape in mathematics that you might recognize more simply as a donut. Typically it's drawn something like this. Let's see if I can do this a little better here. So I hope you can see that this is a donut shape now. So you can take a circular cross section. If you were to cut right here, you would end up with a circular cross section cut out of like a donut or a bagel. And you could also slice it a little more traditionally like a bagel down this direction. And you would also see that you would have a circle around the center and a circle around the outside. So think of a donut shape, think of a ring shape, think of a bagel, something along those lines. The cross sections are circles all the way around. And in order to describe this shape, we describe it with two different radii. Two different radii. The first one is when we measure from the center of the torus here to the center of the actual part of the donut that you would eat, right? And this is called capital R. It's the large radius. And then we also have lowercase r, which is the small radius along this side. So lowercase r measures from the center of the part of the donut you can bite to the outside of the part of the donut that you can bite. Whereas capital R measures from the center of the donut hole to the center of the donut here. So why is this important? Well, if you imagine this orange circle here is the region R that we're interested in for the theorem of Pappus. This is now being rotated around a line which is like the big central axis of this torus here. Right, so imagine a big axis going around the middle here. We're going to take this circle R and we're going to rotate it around the blue line. That is going to create the volume of the torus itself. So we can find the volume of the torus using this formula here. If we know the distance that the centroid of this circle traces around this torus, and we know the area of the circle itself, we can find the total volume of the torus here. Okay, so how much distance does the centroid trace? Well, the nice thing about circles is that the centroid is exactly at the center. So the center of this circle is going to trace out a path that goes all the way around this torus this direction. It's going to trace out a circle with a radius of capital R. So D, the D from this line right here, D is equal to the circumference of a circle with capital R radius. That's going to be 2 pi capital R. And then A, the actual area that's of the circle here itself, maybe I'll do this in green here, the area of the circle itself is going to be pi times little r squared. So if I want to find the total volume of the torus, the total volume of the torus can be found by multiplying these two quantities together. We're going to take pi r squared and multiply it by 2 pi times capital R. And if we reorganize these a little bit, factor the constants out front, the volume is going to be 2 times pi squared times little r squared times r. This is the volume in general of a torus. So you can see that increasing the big radius, making your torus wider this direction, is going to increase the volume. But increasing the radius, the small radius here, is actually going to increase the volume much more quickly. And then 2 pi squared is just a constant multiplied out front there. Whew. Okay, so this is the theorem of Pappus. In general, this is usually only useful when the centroid is really easy to find for your shape. So in this case, we had the easiest centroid in the world. When you have a circle, this is the most symmetric shape there can possibly be. You know exactly where the centroid is. So you can multiply that by the distance that travels by the area and find the total volume here. In most cases, finding the centroid is actually a much harder challenge, right? So you might as well just calculate the volume directly. But in this case, and in some other special cases, it's relatively easy to find the centroid, and so you can go ahead and use the theorem of Pappus to find these volumes. Whew. Okay, so that is it for section 8.3. I'll see you guys in class on Wednesday.